Well, welcome to the 12th lecture in the Radar Systems Engineering course, Clutter Rejection. And this lecture is going to be really two lectures, Basics in Moving Target Indication, and then we're going to have a part 2, which will be lecture 13. Because it's such a meaty subject, we're going to put two large lecture sections on this issue, and it's even going to grow out further. And today here in New England, we're about 48 hours from Hurricane Irene hitting. It's a Friday afternoon at 3 o'clock, and we won't have power, I can guarantee you, in 48 hours. If any place in New Hampshire loses power, our street loses, well, the feeder street from us loses power. The side street that we're on has underground power, but nothing will be coming through. So what I'm going to try and do is record as much as I can in the next 2 days, and hopefully lectures 12 and 13, and then after the hurricane and we get the power back, and then I'll edit it, and we'll move on from there and get those lectures up on the web. Okay, now here's our block diagram of the radar again, and here's the section we're going to work on: clutter, rejection, and Doppler filtering. Now, I spent an enormous amount of time in the last 2 lectures ago on radar clutter, describing the big problem. Because if it wasn't for radar clutter in all of its different forms, a pulse of energy would go out, hit the target, it'd come back. You remember from those PPI displays, you'd just see targets. You wouldn't see anything else. And the prime object of radar, one of the biggest and toughest things, is to see deeper and deeper into the clutter so that radars will work very well in high clutter regions, and particularly as targets get smaller. And as you'll see later on in the lecture after that, with airborne radars, the clutter rejection problem is a very difficult one. We're going to put a whole lecture on that. So here's this whole area of signal processing. After we've done the pulse compression, we're going to do the clutter rejection, and I'm going to start just from scratch and build it right up so that you can see where we are today. Okay, Steve Wien is a great friend of mine. We were undergraduates at MIT together, and he thought it'd be great one time when he was teaching the radar equation lecture, and I was teaching some of the pulse Doppler stuff. You know, there's 2 ways to handle noise, to get your signal to noise ratio up, signal to noise and clutter. Well, there's power. You can get more power and more aperture, more power in your transmitter and more aperture. But you got to use finesse in signal processing. That is to say, you have to use a lot of intellectual property and very high technology and high-speed processing. And we put this together years ago. Steve's still about the same stature, and I like to look at this because I'm about 40 pounds lighter. And we added this thinking about what we were thinking at the time, to add a little humor into things. This isn't the same blue shirt, but it's the neck size is a lot smaller than the one I'm wearing than that one is. Okay, what I'm going to do is break this lecture up into a couple of different sections. This is going to be the first section I'm going to talk about in 3 20-minute or so pieces. We're going to have an introduction. We're going to look at the history of clutter rejection, non-coherent MTI, moving target indication. That's getting rid of the clutter as best you could without using phase information for pulse to pulse. And then look at an incredible thing that was a byproduct of the digital revolution, of Moore's law. And what that did is that enabled us in the radar community to do orders of magnitude better in the job of rejecting clutter, suppressing it, and seeing very weak targets in the clutter and in heavier and heavier clutter. And then we're going to spend the next two pieces of this lecture looking about MTI cancellation techniques. Then finally we will summarize this MTI portion. And the reason you might say, well, there's another part of it you'll see, pulse Doppler processing, and that MTI techniques are used in many radars in the field right now, and it's good to see that evolution, and it shows you how the Moore's Law came into play, and we'll spend some time looking at that. Now let's just remind ourselves of this horrendous problem we have. We throw around, well, first let's look at ground clutter. Here's that naval radar scenario, and we've got ground clutter. It's the most intense usually, and it's discrete a lot of the time, and it can be 5 or 6 orders of magnitude greater than the target. And the target I'm using here is, I call it a Piper Cherokee at 1 square meter, a standard target that an air traffic control radar would see at 60 miles. And it's designed to see and does see. And the Doppler velocity is 0 for ground-based radars, and the spread is relatively small. And then we've got sea clutter. It's less intense than ground clutter, because usually radars on ships will look down close to the ground as well as down close to the sea as well as in the air, and there'll be echoes from the sea. And they're less intense than these numbers by 20 or 30 dB, and often it's quite diffuse. And we'll tell you, because I showed you, the sea just goes on, and it's sea state 1, 2, 3, 4. We'll probably have sea state 6. We're 5 miles from the coast of New Hampshire, over by the seashore. So we're got 10, 15 miles out to shore. They're going to have some pretty big waves. And Doppler velocity varies for the ship-based radars, because what we're talking about is the relative motion. The Doppler velocity that the radar on the ship would see is the relative motion of the target relative to that radial velocity relative to that of the ship. And the ship could be moving away or back and forth, and then you can have the targets moving, of course. But the clutter itself is going to vary with the velocity of the ship, because the ocean has its motion, and the Doppler spread is moderate there too, and remember it increases with wind speed. Now with rain clutter, that's a diffuse windblown clutter, and we're going to get to see a picture of the PPI with all of it. It can be 1,000 times greater than the target, and its strength and frequency are very dependent on the time of day and whatever. Later on, I'll try to sneak in a picture of Hurricane Irene in the Pulse Doppler section to show you what an up-to-date picture of it looks like. It's very, very intense is the backscatter from the rain. They're talking about 10, 15 inches of rain instantaneous near the eye of the hurricane. But normally 4 or 5 millimeters an hour. And the rain has a Doppler velocity that varies relative to the wind and the radar velocity. And there's a spread that's moderate. And then there's bird echoes, and I think the birds aren't going to be, they're going to be down close to the ground, on the ground for this coming hurricane. But there can be hundreds or tens of thousands of birds in the coverage of a radar. And their velocities are 0 to 60 knots. The flocks can fill the whole region, 0 to 60 in Doppler space. And they're a very big issue for small targets, for very small targets. Now here's that PPI display. And here are 2 targets. I'm going to look at this area blown up a little more. And what we want to do is to get rid of this, what appeared to be the ground and rain. Now, the first thing that occurred to people who built radars and put PPI displays up is they would say, looking from scan to scan, that the ground doesn't move. So if we took a whole scan of data and then subtracted the next scan of data from it, we'd be left with the targets which physically move, as these do. And these point sources of clutter don't move. And that's just what people did, only they didn't have an easy way to store all this data. And what they used to store the data, we'll get to see in a moment from the history of things. Now, the solution to get rid of all these problems are moving target indicator, MTI, and pulse Doppler processing using the Doppler shift of the different signals from the targets to enhance detection of moving targets and reject clutter. The total solution is a sequential set of Doppler processing and detection/thresholding techniques. And remember, smaller targets, you're going to need more clutter suppression, because you want the signal to output, the ratio of the signal power to the clutter plus noise. If the targets get smaller, you're going to need more clutter suppression. So clutter suppression as well as noise suppression are very important for smaller targets. Now let's look, because we're going to be using the Doppler effect a lot in this. I wanted to go over with care with you the Doppler effect. We have a transmitted burst of a sine wave, and we've got a target out here whose range is R of t is equal to its initial range minus Vt. Say it's moving in this direction. And here's the transmitted signal. The signal is the transmit signal is a function of time. It's got an amplitude as a function of time. For this case, it's just a step function, 0 everywhere but in this region. And it's got we're looking, of course, here at the real part of the signal. It's a complex sinusoidal, the electric field, and of course the magnetic field perpendicular to it. And here's the received signal. Notice it's attenuated by the fact that it goes out and comes back, and there's a time tau, a time delay that the received signal comes back and forth, and that time delay is just twice the range to the target divided by the speed of light. And then there's the wave coming back, and you've got an added frequency in the frequency of the wave, the Doppler frequency. And the amplitude of the backscattered wave, as I said, is very weak, and the delay is proportional to the distance you are from the target, so you get a direct measurement of range, and the frequency of the received signal is shifted by the Doppler effect. And here is the Doppler frequency. It's twice the radial velocity times the carrier frequency of the radar. Like this was an S-band radar, the frequency would be 3 gigahertz divided by the speed of light. And for approaching targets, it's plus, and for receding targets, it's minus. Now I'd just like to go over a few terminologies and the basics of how we get rid and suppress clutter. The techniques can be divided up into two techniques: moving target indicator techniques and pulse Doppler techniques. And they each have different characteristics, as you'll see, and we'll go over them one at a time. Moving target indicator techniques, so-called MTI techniques we call them in shorthand, suppress the clutter with a high-pass Doppler filter. That is to say, they suppress the clutter, mostly that's ground clutter, that has zero or very near zero Doppler velocity, and they pass the rest of it. They reject slow-moving clutter, and they detect moving clutter. Typically, 2 or 3 or 4 pulses, mostly 3 pulses these days, are used to in this type of processing. And with these type of processing, and it being a high-pass filter, there's no estimate made of the target's velocity. We'll see that in pulse Doppler techniques, an estimate is made of the target's velocity because we're going to be using bandpass filters, and with those you want to suppress a certain Doppler velocity or Doppler frequency, and then see a certain band, and then suppress on the other side. And that idea of building up big suppression, and then a little pass band, and then big suppression is something that you need a lot of pulses to do it with. And it's going to come into play into how we design the different processors. So pulse Doppler techniques suppress clutter with a set of passband Doppler filters. What they'll do is they'll take data from a set of pulses, put them into a linear Doppler filter, which will have different weights. And those weights will have each, the inputs will all go into a set of filters. A filter bank, we call it. And the weights on each of those filters will be designed so that they will pass certain bands of radial velocity and suppress all others. The targets are sorted into, as this implies, one or more Doppler filters, and therefore we can estimate directly the radial velocity of the target. And large numbers of pulses are coherently processed so that we generate an optimum set of linear Doppler filters. And the number of pulses that you can use for a low PRF radar, the minimum number you really need is about 10 to get good suppression on the sides, because the things that you want to suppress on the side is going to be rain. And 10 is what you need to really suppress it and get the side lobes down low. And airborne radars with we're going to have a whole lecture on airborne radars. You can do thousands of pulses in very high PRF modes because of the different environment and the motions of the sensor and things you'll come to see in the airborne signal processing lecture. Now, this lecture is going to study moving target indicator techniques, and we're going to go over it in detail. You might say, why? Because there's an awful lot of radars out there in the country, air traffic control radars, that just use moving target indicator technique. Those techniques, which are in use today and will be in use for many more decades, many of them, before they're taken over by new technology. Just because when you have a new technology available, you just don't go out and get it. It isn't something like, first we had cell phones, and then you could take a camera, take picture, and then you could do all texting and all sorts of new features, and you go buy a new one. Well, when you buy an automobile, most people don't buy an automobile every year when they come out with some new feature to the automobile. You buy it for a long time. And I think I saw one time 85% of the Toyotas ever built over decades are still in use. And that's why we want to study techniques that you wouldn't build it with today, but are present there today. Now let's look at the history of clutter rejection. Now here's what a PPI display would look like. You see right there a target. This is a fluorescent analog screen, and there's no clutter in this particular screen, and in time the fluorescence dies. And we generate, this is the upper left-hand corner of that PPI screen you saw before. And it's used again and again. It's a map-like display, radial distance to the center, marked off in range, and the angle of the radius vector is the azimuth of the target. It's like you're looking down upon from high up above the radar, you're looking down. And this would be a rotating antenna. And when you apply a threshold crossing to get detections. The earliest clutter, backscatter rejection techniques consisted of storing all the data from the pulse of radar echoes and from the next pulse of echoes. And the storage devices were very crude by today's standards. Block diagrams here are of CW and pulse radars. With a CW radar, you just keep transmitting FT, and what comes back is not only energy at the transmitted pulse, but the Doppler shifted, either if the target is coming or going, the Doppler of the target, frequency of the target, is added or subtracted. It's just an infinite CW or semi-infinite CW waveform. This is just about like your police radar. You have a CW transmitter. And then you'd have a filter which would cancel out, break away off the transmitted pulse, and you'd come into a receiver where you could separate these two and just have the Doppler coming in and send it through a Doppler filter that you could that was adjusted along with some other electronics to digitally tell you how far the Doppler was. And what you can and that's what the policeman reads. A basic pulse radar, on the other hand, sends out pulses of CW waveforms, many of them. In this case, 3. There's a transmit-receive switch, and then the received data goes into the receiver, where it is mixed with the CW oscillator, which generated, it's at the frequency of the transmit pulse. It comes out with you just see the Doppler frequency of the target, plus or minus 0, just the Doppler frequency. And then you send this data into a Doppler signal processor, and then afterwards you send from successive scans data into a tracker to correlate them, to follow the track of the target you're looking at. And of course, if the target was receding, it would have a minus sign. And notice before it was coming towards you, it's receding and approaching, you can see. Here it would subtract. Okay. Now, quickly summarizing probably 20 years of radar technology, stability was a great problem. It was very hard to obtain sources that had the stability to use phase information as accurately as you needed to get rid of all of the, to do the subtraction to the level of cancellation that you'd like. And delay line cancelers, as I mentioned, were used, and the materials used were quartz and mercury. So what they would do is have a long tube of mercury, and they would send the pulse in and transform that pulse into an acoustic wave into this mercury medium through a transducer to send the wave down a significant length of mercury And since the velocity of an acoustic wave is 1/10,000th that of an electromagnetic wave, you didn't have to have a 50-mile length tube. You could drop it way down. Quartz delay lines used polygons of quartz that had reflected signals where there'd be an input transducer, the wave would go over and there'd be a partially bent surface so that the wave would go back and forth and back and forth and back and forth acoustically and then finally out. And it was more stationary. The disadvantages are secondary waves that can be set up in these devices. There are large insertion waves, and the dynamic range limitations of analog displays in general also cause the signals to be limited. That is to see, when you were near a very large piece of clutter, the dynamic range of your display was only 20 dB, and if you had a target bigger than that, you could see the big target by turning your gain up nicely, but you couldn't see the small targets at the same time. So the analog displays were another limiting factor. In the mid-70s to the present, the digital revolution has happened, and far more. This is when things took off. It's like a space travel didn't happen till Sputnik. In 1957, boom, it started. It's that kind of a thing. And in the mid-70s, although the integrated circuits had been built, it took a while for them to get up to speeds so that they could be used for digital signal processing techniques. They were already being used in mainframe computers, but you needed much higher speeds to get them to work in signal processing systems. And memory capacity also had to get up there, so it was cost-effective too. So you have to have cost-effective processor speed and memory capacity. And they're continually increasing, and this cost spiraled downward to the point where affordable complex signal processing were more and more easy and less expensive and affordable. Now let's look at the impact of the digital revolution. The three technologies have evolved and revolutionized radar processing over the past 40 to 50 years. Coherent transmitters, the ability to have A to D converters to convert the analog return into with a high sample rate linearly over a wide dynamic range. And the ability to do that was along with the digital processing revolution, Moore's law, low-cost compact digital memory and processors. That development in the technology area, along with, and I can't understate this, the development of the algorithmic formalism to practically use digital signal processing hardware and to develop the hardware. And that, I think the first book that I saw in about 1970 was a book by Gold and Charlie Rader, Ben Gold and Charlie Rader at the lab. It was a little too dense, but it had it all there. Alan Oppenheim at MIT and one of his, Charlie Rader and Ben Gold were at the laboratory. They're long since retired. I think Charlie might be doing some part-time work. But in any case, Alan Oppenheim, a professor at MIT who had been out at Lincoln Laboratory in management positions, he went back to being a professor, and Schaefer, one of his students, put together a book called Digital Signal Processing. And that book was a milestone in putting together for students the algorithmic formalism of digital signal processing with problems that you could take as a course It was first given to grad students, and now undergraduates take it toned down. It's a very hard book, Alan Oppenheim and Schaefer is, and they've written many, many editions. And also a book by Gold and Rabina, Larry Rabina, who was actually in my dormitory at MIT. He was at Bell Labs, and Ben Gold was a group leader at Lincoln Laboratory, and they put together the first real solid volume at the same time as Oppenheim and Schaefer, books on digital filtering, how to implement digital filters with this new hardware that we had available. And these developments have been the technology enablers that have been the key to the development of modern, I'll say the beginnings, because the A to D converters, the transmitters have gotten more stable. The A to D converters have had wider dynamic range, linear, but they got it together so that you could put the first packages together to do radar signal processing and really see it work wonders on the simpler cases in air traffic control radar. And after that, there have been leaps and bounds since the 70s in this signal processing revolution for radar. These developments, as I said, have been the key technology enablers for the initial key technology enablers for today's modern radar clutter rejection techniques. Okay, I'm going to take a break now, and then we'll go on to the next section.